Tonight we'll spend some quiet time with a rare guest in our sky's 3-eye atlas. It is an object that came from another star system and is only passing through once before heading back out into deep space. If these calm science stories help you relax, a like or a subscribe will help others find this peaceful corner too. Here asks the question to hold in mind. What does a traveler from another star leave behind when it only visits once? 3-eye atlas is one of those travelers. It was born far away, circling a different star, until something pushed it loose. Its orbit is hyperbolic, meaning it doesn't circle back like local comets. It enters, swings around the sun, and then continues on forever. That's why it matters. Each interstellar visitor is a sample from another solar system. Its light, its color, and its path tell us what it's made of, how it was shaped, and how small worlds can be ejected into space. A few quick terms help. A coma is the fuzzy glow around a comet when sunlight warms its ice. Magnitude measures brightness. The lower the number, the brighter it looks. Non-gravitational forces are tiny pushes from gas jets, like natural thrusters, that can slightly shift its orbit. The story tonight includes how 3-eye atlas was found, how astronomers track its speed and path, how telescopes notice faint moving points, what its orbit means, and how it compares with earlier visitors, 1, Oumuamua, Mua, and 2-eye, Borisov. We'll also look at what instruments are ready for the next discoveries. So what does it look like to us? Astronomers first see it as a dim dot, sliding slowly against the background stars. Survey telescopes take repeated short images, and software looks for movement. The stars don't budge, but the visitor shifts. String those frames together, and its track appears. From there, scientists calculate its orbit. The key number is eccentricity. Less than 1 gives closed orbit. Exactly 1 gives just at escape speed. Greater than 1 gives open path. For 3-eye atlas, the value is well above 1. It's not staying. Sunlight may make it glow with a coma, or even a thin tail, which always points away from the sun because of solar wind. Some interstellar bodies stay bare, looking like plain rocks. Either way, the way its brightness changes as it spins tells us about its shape and rotation. Filters reveal its colors clues about whether it's dusty, icy, or rich in organics. Because it comes from outside our system, its speed is higher than local comets. That speed still reflects the pull of its home star, added to the sun's influence as it passes by. It looks unusual, but it follows the same physics. Its name also carries meaning. 3-eye means it's the third confirmed interstellar object. An atlas honors the asteroid Terrestrial Impact Last Alert system that discovered it. Atlas scans the sky nightly, looking for objects that could threaten Earth. But along the way, it also finds rare visitors like this one. The process is careful. Astronomers record precise positions and brightness over many nights. Other observatories cross-check the data. Early orbit estimates can be rough, but with more observations, the path sharpens. Small pushes from gas jets are also included in the calculations. In the end, the picture is clear. 3-eye atlas is an icy body from another star system passing through once. It might glow faintly, it might not. But its orbit proves it isn't bound to the sun. The I in its name marks it as interstellar, and the number 3 places it after 1-eye Oumuamua and 2-eye Borisov. By this third discovery, it's obvious these are not accidents. They're part of a wider pattern. Each one carries a piece of another solar system, reminding us that the universe is more connected than we once thought. The science that follows grows from a simple starting point. A name like 3-eye atlas is more than just a label, it's also a guide. It points us directly from the name to what it means, without extra confusion. To study objects like this, astronomers use a few basic measuring tools. The first is distance. The standard unit is the astronomical unit O, the average distance from Earth to the Sun, about 150 million kilometers. That can sound enormous, so let's break it down. The Earth-Moon gap is about 380,000 kilometers. Think of that as 1 ruler. The Sun is about 400 of those rulers away. Light travels 1 astronomical unit in roughly 8 minutes, so when you see sunlight on a lake or the ocean, the photons you're seeing left the Sun about the length of a song ago. The second tool is speed. It's measured in kilometers per second. Earth orbits the Sun at about 30 kilometers per second. That means every second, we move the distance of a short commute. Planets farther from the sun move more slowly. The ones closer in move faster. Interstellar objects often carry extra speed from their home systems, so when they arrive here, they may be traveling at tens of kilometers per second compared to the sun. These are reckless speeds, just the natural result of falling through gravity while already in motion. The third measure is brightness, tracked on the magnitude scale. This is an old but reliable system where smaller numbers mean brighter objects. Each step equals about 2.5 times more light, and a 5-step difference works out to about 100 times brighter. That's why Venus has a negative magnitude, while faint comets may be in the positive teens. It may look backwards, but the scale lets astronomers compare brightness very precisely, even through less than perfect skies. With these rulers' distance, speed, and brightness, the idea of unbound becomes clear. Orbits are a balance between kinetic energy motion and potential energy gravity. If the total is negative, the object is trapped in an ellipse. If the energy is exactly zero, the path just skims the escape line. If the energy is positive, the traveler bends around the sun once and never returns. The number that shows this difference is eccentricity. Circle has eccentricity 0. An ellipse is between 0 and 1. A parabola, right at escape, is exactly 1. A hyperbola. The open curve of a true visitor is greater than 1. For 3i Atlas, the value is safely above 1, and that's what marks it as interstellar. 2 anchor distances. Jupiter orbits at about 5 astronomical units, Neptune at 30 astronomical units. The asteroid belt is mostly between 2 and 3 astronomical units. And the Kuiper belt extends to about 50 astronomical units. Beyond that, the Oort cloud may reach tens of thousands of O. You don't need to memorize the numbers, just think of them as milestones. The inner system, the middle zone, the far frontier, and the frozen halo beyond. For speeds, here's a comparison. Earth's 30 kilometers per second orbit could carry you across a continent in just minutes. At Earth's distance, the sun's escape speed is about 42 kilometers per second. Any slower object is trapped. Anything arriving faster can swing past and continue outward. The leftover is called the hyperbolic excess speed the motion. An interstellar object keeps even after the sun's pull. Brightness ties in too. As a traveler nears the sun, it reflects more light and may brighten. If surface ice vaporizes, a coma and tail can form, boosting its glow. At the same time, distance dims light, since doubling the distance spreads brightness across 4 times the area. By following how brightness rises and falls in light curves, astronomers uncovered details about distance, surface activity, and rotation. Altogether, O for distance, kilometer per second for speed, magnitudes for brightness, and eccentricity for orbit. These simple tools turn a mystery into clear measurements. Now, how do astronomers find something like 3i Atlas in the first place? Wide-field surveys scan a region of sky, pause, then scan again. Stars stay still, but moving objects shift. With just a few images minutes apart, software can flag that tiny drift. Several exposures linked together form what's called a tracklet, a short arc showing direction and speed. But a single tracklet isn't enough. To confirm, astronomers need more, across several nights. They submit positions and times to the Minor Planet Center, which posts candidates for follow-up. Telescopes worldwide then check the object before it slips away. Smaller observatories add more tracklets, while larger telescopes can lock onto the faint moving dot. For the hardest targets, astronomers stack exposures, shifting each frame so the object lines up, making it stand out against background noise. As more data arrives, the orbit solution sharpens. If the curve is closed, the object is local. If it hugs the escape edge, more data is needed. But if it consistently demands an open hyperbola, eccentricity above 1 confirms it's interstellar. Precovery images older photos where the object was accidentally captured, can stretch the timeline and make the orbit even more precise. Surveys like Atlas, Pan-STARRS, Catalina, and Zwicky Transient Facility are built for this work. They scan wide fields, repeat often, and use automated pipelines to catch faint movers. Once enough observations agree, the object earns a provisional label. If the orbit clearly requires interstellar energy, it gains the I designation, 3i Atlas, that path from faint points of light to global follow-up to eccentricity greater than 1 was the road to confirmation. In the end, discovery is a team effort. It isn't a single image that makes the case, but the rhythm of repeated looks linked together, checked by many groups. Out of thousands of quiet frames, a clear story emerges. A point of light shifting in just the right way to prove it came from beyond our solar system. At Earth's distance, remember, the sun's escape speed is about 42 kilometers per second. While Earth itself moves at 30 kilometers per second, a little extra push is enough to set something free. Interstellar objects like 3I Atlas arrive, already carrying that extra hyperbolic excess speed. Gravity bends their path but cannot capture them. That's why their orbits take the shape of hyperbolus, the one curve that marks a true passerby. And for 3I Atlas, its eccentricity greater than 1 is the unshakable proof is a traveler from another star. Astronomy often begins with a few simple but powerful tools. The first is the astronomical unit, this is the average distance between Earth and the Sun, about 150 million km. To give it perspective, the Earth-Moon gap is about 380,000 kilometers. If you treat that distance as a small ruler, the Sun sits about 400 of those rulers away. Light crosses one astronomical unit in roughly 8 minutes, which means the sunlight you see now actually left the Sun about the length of a song ago. The second tool is speed, measured in kilometers per second, kilometer per second. Earth orbits the Sun at about 30 kilometers per second. Every single second, our planet moves as far as a short drive. Outer planets travel more slowly, while inner ones move faster. When objects arrive from another star system, they often bring extra velocity from their original homes. That's why they may approach at several tens of kms compared to the Sun. To us, it sounds extreme. But in space, these speeds are completely natural. The third measure is brightness, recorded on the magnitude scale. In this system, smaller numbers mean brighter objects. A one-step drop equals about 2.5 times more light, while a difference of 5 steps equals about 100 times. That's why Venus carries a negative magnitude, while faint comets may be in the positive teens. The numbers may look upside down, but the system allows astronomers to compare brightness precisely, even in poor conditions. Now, let's talk about what it means to be bound or unbound. If an object's total energy is negative, gravity traps it in a closed orbitan ellipse. If the energy is exactly 0, the object sits right on the escape line. But if the energy is positive, the object isn't coming back. Kit swings past the Sun once and then leaves. The number that marks this difference is called eccentricity. A perfect circle has eccentricity 0. An ellipse falls between 0 and 1. A parabola, exactly at escape, is 1. A hyperbola. The open curve of a visitor is greater than 1, for interstellar objects like 3I Atlas. Having eccentricity greater than 1 is the clear proof that they came from beyond our solar system. To place distances in context, Jupiter orbits at about 5 astronomical units. Neptune at 30 astronomical units. The asteroid belt sits between 2 and 3 astronomical units, while the Kuiper belt reaches to around 50 astronomical units. Beyond that, the Oort cloud may stretch tens of thousands of O. You don't need to memorize these values, they simply mark the inner system. The middle belt, the outer planets, and the far icy shell. Speeds also set the stage. Earth travels at 30 kilometers per second, but at our distance from the Sun, the escape velocity is about 42 kilometers per second. Anything slower is trapped. Anything faster can pass through and keep going. That leftover speed is called hyperbolic excess velocity, and it's what interstellar travelers carry when they arrive. Brightness plays a role too. As a comet gets closer to the Sun, it reflects more light and can brighten. If surface ice turns to gas, it releases dust that creates a glowing coma, increasing brightness even more. But light also fades with distance, double the distance, and brightness spreads 4 times weaker. By tracking how brightness rises and falls in light curves, astronomers uncover information about distance, rotation, and even surface properties. Discovering faint travelers like 3I Atlas takes coordination. Wide-field surveys such as Atlas, Pan-STARRS, Catalina, and the Zwicky Transient Facility scan the sky again and again. Software looks for points of light that shift while background stars remain fixed. These movements are linked into a tracklet, a short arc showing speed and direction. One tracklet hints at something, but several are needed to define an orbit. Once data is collected, astronomers send positions and times to the Minor Planet Center, which alerts observatories worldwide. Because these objects move quickly, follow-up is urgent. Smaller telescopes add more tracklets, while larger telescopes track faint objects precisely. Sometimes astronomers even stack multiple images to make the moving dot stand out against background noise. As data builds, the orbit becomes clearer. If eccentricity remains above 1, the object is confirmed as interstellar. This doesn't happen in a single night. It takes teams across the globe reaching the same conclusion. Astronomers also search through older photos for what are called precovery or unnoticed appearances of the object. Even one precovery can sharpen the orbit dramatically. Escape velocity ties it all together. At Earth's distance, it's 42 kilometers per second. Earth itself moves at 30 kilometers per second. Add a little more speed, and you can escape the sun's hold. Interstellar visitors like 3I Atlas already arrive with that extra hyperbolic excess speed. Gravity may bend their paths, but it cannot capture them. Their hyperbolic orbits with eccentricity greater than 1 are the unmistakable proof. In the end, discoveries like these depend on rhythm and teamwork. Surveys scan the sky, software detects movement, telescopes confirm, and mathematicians refine the orbit. From what begins as a faint shifting point of light, the story of an interstellar traveler unfolds, a reminder that now and then visitors from other stars pass through our skies, leaving behind a traceable path and a piece of wonder. Small pushes can change the path of a comet or interstellar visitor. A push in the direction of travel works like tapping gently on a car's accelerator, or brake it stretches or shortens the orbit slightly, or sideways push tilts the path. These forces are extremely weak, but over time they add up. Gravity provides the main pull, yet these faint thruster-like nudges fine-tune the final course. How weak are they? Millions of times weaker than Earth's gravity, and only a tiny fraction of the sun's. Imagine the light touch of a feather, you'd hardly notice it. But with the right tools, astronomers can measure the effect. Outgassing is strongest when ice is warm and vent gas, and it fades when they quiet down. The type of ice matters. Water ice reacts near the sun, while carbon dioxide and carbon monoxide drive activity farther out. This means a single object can look active in one part of its orbit, but calm in another. To study this, astronomers use models. They start with gravity, then add 3 small terms to represent forces in each direction. These terms are scaled by distance from the sun and adjusted depending on which ices dominate. Observed positions from telescopes are compared with predictions, and the models are tuned until the tiny accelerations line up with reality. But measuring is never simple. Telescopes blur the comet's light, and if a coma is present, the glow spreads unevenly, shifting the measured center slightly. To correct for this, astronomers compare the comet's profile to nearby stars, adjust their measurements, and apply careful fits. Each telescope has its own quirks, so results are checked across many instruments, and outliers are given less weight. Outgassing can also twist a comet. If vents are unevenly placed, they act like torques, changing how fast it spins. Over weeks, the spin period can shift, sometimes causing surface pieces to break off. As the spin changes, sunlight reaches new areas, altering which vents are active. That's why comets can behave differently before and after their closest pass to the sun. Other gentle forces exist too. Sunlight itself pushes on small dust particles through radiation pressure. For a solid nucleus, this is minor, but for tiny grains, it's significant. Heat can also cause a recoil force, known as the Yarkovsky effect, though for active comets, outgassing is usually the stronger influence. Radiation pressure mainly shapes the dust tail. Because these effects are so faint, uncertainties matter. Star catalogs contain errors, the atmosphere distorts images, and comet trails can smear across pixels. To handle this, orbit solutions use covariance methods that track how errors connect. Teams test by removing data and refitting, and independent groups run their own checks. When multiple teams see the same small acceleration, confidence grows. Some models also allow for activity that lags behind sunlight or split behavior into inbound and outbound phases, since surface layers can change over time. Why does all this matter? Detecting a push proves that gas is escaping, even if the coma isn't obvious. The direction of the push reveals where vents may be and how the body spins. Strong pushes away from the sun point to daytime activity, while pushes along the path suggest vents that peak slightly before or after local noon. Measuring thrusts also shows how much material is leaving the surface. And if no non-gravitational effect is found, scientists can still place an upper limit on activity. Differences between teams often come from technical details like weather, camera settings, or coma shape. For interstellar visitors, these tiny nudges turn into valuable clues about surface layers, chemistry, and spin. Compare the three known cases. One Eye, Oumuamua, was puzzling. It was seen only after its closest approach showed no clear coma or tail, but its brightness varied as it spun. Its orbit revealed a small, non-gravitational push, likely from faint outgassing or radiation pressure. With little time to observe, many mysteries remain. To Eye, Borisov was the opposite, a textbook comet. It arrived with a bright coma and tail, became more active near the sun, and displayed familiar chemistry. Its nucleus looked much like known comets, and it was tracked for months by amateurs and professionals alike. 3. Eye Atlas sits between them. Its hyperbolic orbit confirms it came from beyond the solar system, tilted strongly against the plane of the planets. Its brightness and color suggest mild activity, depending on its surface. It won't dazzle the naked eye, but careful measurements still reveal plenty. Together, these three visitors show that interstellar space sends us a mix, some quiet, some active, and some in between. The key is not whether a tail appears, but the orbit itself. Eccentricity greater than 1, and energy high enough to escape the sun. Timing also matters. Oumuamua was found late, so observations were limited. Borisov was caught earlier, giving astronomers a long window. Atlas benefits from today's faster surveys and better coordination. Discovery not only adds knowledge but improves the way we study the next. Placed side by side, they form a small family portrait. One mysterious, one classic, one modest but instructive. Together, they prove that other star systems launch out many different kinds of small bodies, and that every so often, one crosses into our sky, offering a rare glimpse of another world. The faint glow of 3-Eye Atlas isn't a showpiece in the sky, but it's still rich with information. Its brightness rises as it nears the sun, just as simple geometry predicts. Subtle shifts in that brightness reveal rotation, while the size of those flickers suggests the object isn't perfectly round. Colors lean toward a muted red, the kind often seen on old dusty bodies exposed to cosmic rays and tiny impacts for countless years. Put together, these details describe a small weathered world with a crust, moving quietly through our solar neighborhood on a one-time visit. From there, the debates begin. One question is whether it's active. Some images hint at a thin dust halo around the object, while others show nothing at all. So the difference isn't about errors, but about viewing conditions, equipment, and geometry. If faint gas jets exist, they could nudge its orbit slightly, but proving that requires months of precise tracking from many observatories. Getting clear spectra is tough for such a dim visitor. A few color measurements point to dust, while others leave room for buried ices like carbon monoxide or carbon dioxide. With so little time to observe, scientists can't yet pin down its exact chemical makeup. Size is also uncertain. Astronomers estimate it from brightness, but that only works if we know how reflective the surface is. A dark object would have to be larger to reflect the same light, while a brighter one could be smaller. For now, we only get a size range, not a precise figure. Its spin is tricky too. The light curve suggests possible rotation periods, but different solutions fit the limited data. Outgassing can also change how the object flickers, making the pattern harder to lock down. More coordinated observations are needed to settle the question. Even with these open questions, the essentials are firm. 3-Eye Atlas came from interstellar space. It will swing past the sun safely, and it poses no danger to Earth. It probably carries ices, like many small bodies formed in cold regions, but activity appears mild at best. Its reddish tint and dim behavior mark it as part of the family of dusty, weathered objects. Future data could sharpen the picture. Better spectra during peak visibility might detect faint gases or confirm their absence. Long-term positional tracking could show whether outgassing is altering its orbit. Coordinated light curve campaigns would narrow down its spin and shape. Extra techniques like polarization studies, archival image searches, and thermal infrared measurements could refine its size and surface properties. Importantly, the lack of drama is itself a clue. A weak coma suggests either a tough crust or ices that need stronger sunlight to release gas. A near-stellar profile most nights points to low dust production. Small flickers in brightness still whisper about its shape and spin. Science here depends on patience, careful calibration, and respecting error bars. Even when the signal is faint, each measurement adds to the record. The faintness itself has a simple cause. Earth's atmosphere glows, the moon and cities add background light, and detectors carry noise. To overcome that, astronomers take long exposures or stack many short ones, aligning the images on the object so it sharpens while stars streak. Brightness is then measured either by summing the light in a small circle or by modeling the spread of light, sometimes both. Even non-detections matter, since they rule out stronger activity that would have been visible. What emerges is a consistent picture. Interstellar in origin, safe in its path, modest in its activity, reddish in tone, uncertain in size, and still puzzling in rotation. The unknowns are about degree, how much activity, how large, how reflective, not about its nature. As for origins, objects like 3I Atlas likely formed in young planetary systems. Beyond the snow line where ices could build up, many were flung out by giant planets or unstable binaries, and some drifted free from crowded star clusters. Over time, cosmic rays and micrometeorites hardened their surfaces, while inner ices stayed preserved. Ejection can happen early in a system's life or billions of years later, and the Milky Way is probably filled with such exiles. By the time they reach us, their exact birthplaces are impossible to trace. But broad patterns remain. Small, cool stars push their snow lines close. Hot stars push them far, and dense clusters eject more debris. Each visitor carries part of that story, shaped both by its home system and its long journey through the galaxy. The physics of escape is straightforward. At Earth's distance from the Sun, an object must move faster than 42 kilometers per second to break free. Earth itself travels at about 30 kilometers per second, keeping it bound. For an interstellar object, the sum of its motion and the Sun's pull is positive, not negative, which means it's unbound. 3I Atlas arrived with extra speed, swung around the Sun, and will leave with the same surplus. It's just aimed in a new direction. No engines, no mysteries, just gravity and momentum at work. In the end, 3I Atlas is faint, but not silent. Every photon gathered adds to a picture. A small, dusty, interstellar traveler passing quietly through, reminding us that the galaxy is full of wanderers, and that patience often reveals more than spectacle. When astronomers talk about escape speed, it's not just a figure of speech. It's the hard boundary that decides whether an object stays tied to the Sun or leaves forever. Picture Earth far to the side as a fast-moving traveler swings past the Sun. The planets can bend the path slightly, but they can't take away the extra energy the object already has. To actually trap it, you need to remove just the right amount of speed at just the right moment, usually through a close pass by a giant planet or with rocket power. For small, icy bodies, nature almost never sets that up. The timing is too exact, and the chance too slim. There are weaker influences, jets of gas, the push of sunlight, or tiny recoils from heat, but compared with the escape barrier, they barely register. These small forces can nudge the timing of an orbit or tilt it a bit. Yet they rarely change the final outcome unless the object lingers close to the Sun while venting huge amounts of gas. The big contest is still between the Sun's pull and the traveler's own speed. The Sun's mass defines how deep the well is. Distance decides how steep it feels. And escape speed is the number that answers. How fast must it go to never fall back? Since the formula depends on 1 divided by distance, moving slightly closer makes escape much harder, while moving outward makes it easier. That is why spacecraft borrow speed from planets to break free, and why planets can also kick natural fragments the other way. Orbit shape tells the same story in another language. Negative energy means an ellipse, 0 means a parabola, and positive marks a hyperbola. The same is echoed by eccentricity. Less than 1 is closed, exactly 1 is balanced on the edge, greater than 1 is open. By measuring speed and distance, astronomers can quickly see whether capture is even possible. When small pushes show up, they can be weighed for importance without fear. A leftover speed above escape speed is not poetry, is proof, a mark of another star. The formula itself is simple. Escape speed squared equals 2 times the sun's pole divided by distance. If the object's energy is greater than that, the orbit stays open. Whatever coma, brightness, or faint nudges appear are just details layered on top. What really matters is the math. Still, the light reflected from these visitors carries its own clues. Astronomers use filters to measure brightness in different colors. If an object shines more strongly in red than blue, it looks reddish. If the two are even, it appears gray. If blue dominates, it shows a faint bluish tint. These subtle shades hint at the surface. Reddish tones are common in comet dust and faraway icy bodies, often darkened by cosmic rays that build complex carbon-rich material called tholins. Fine grains usually scatter more red light than coarse ones, while neutral colors suggest larger grains or fresher ice. A bluish tint may mean fine, fresh dust or unusual minerals. Spectra give more detail by splitting light into its rainbow. Dust creates smooth slopes, while gases stand out in sharp bands. Invisible light, cyanogen, and diatomic carbon are classic comet signs. In ultraviolet, hydroxyl signals water. In infrared, carbon dioxide and carbon monoxide leave clear marks, while sodium glows in a narrow line. If these are present, surface ices are active. If not, gas may be too weak to detect. Dust leaves its own fingerprints. Fine grains scatter sunlight strongly forward, making the comet look brighter when the sun is nearly behind it. Larger grains scatter more evenly. In infrared, warm dust glows near 10 microns, pointing to silicates. But geometry matters. Brightness and color shift depending on the angle between sun, object, and Earth. A sudden brightening at small angles is called an opposition surge. At wider angles, scattering can shift toward red or blue. That's why astronomers gather data across many angles, not just one. Separating the solid nucleus from the haze of dust is a challenge. A coma makes the object look larger than a star. Small apertures isolate the sharp central point, while wider rings measure the dust. Comparing the two gives estimates of nucleus versus coma color. If the nucleus is neutral, but the coma is red, fine grains dominate. The reverse suggests larger particles or a crust shedding coarse dust. Careful calibration, using reference stars, correcting for thin clouds, accounting for Earth's atmosphere is vital. For 3I Atlas, these methods build a picture. A reddish slope would link it with other aged small bodies. A neutral tone might mean larger grains, or a hardened crust. Cyanogen or hydroxyl would prove outgassing, while a non-detection sets limits. Strong forward scattering points to very fine grains, muted scattering to larger ones. Polarization adds another clue. Fluffy grains polarize strongly, while compact grains flatten the curve. Even a handful of observations can sketch a fair portrait. The key is patience. A single pixel of light often blends signals nucleus, coma, fine and coarse grains, fresh ice, and old crust. No single reading is enough, but together they form a consistent picture. A reddish slope plus forward scattering and a silicate glow tells a dust-rich story. A neutral tone with no gas bands and flat scattering points to a quiet surface. A faint cyanogen detection with a tiny orbital nudge points to hidden vents. The portrait is built clue by clue. For 3I Atlas, the likely picture is modest, a slightly red dust tone from age. Faint or missing gas signals, and hints of its makeup drawn from careful measurements. Taken together and checked against geometry and brightness, these pieces reveal material from another planetary system, carried here across interstellar space, and scale puts everything in perspective. Despite dramatic headlines, 3I Atlas never comes close to Earth. Its minimum distance is hundreds of millions of kilometers, confirmed by many observations. Gravity can bend its track but cannot force a collision. Tides at that distance vanish. Earth's tides remain controlled by the moon and sun. The object cannot stop, hover, or park it, moves forward because nothing takes its energy away. It brings no harmful radiation, only reflected sunlight, and perhaps faint dust. Power grids, devices, and people are unaffected. At most, small gas jets may nudge its path slightly, but those shifts are only scientific clues, not risks. Light curves may reveal rotation, and colors may hint at surface chemistry. A weak coma may appear near closest approach, but that is a bonus for observers, not a danger. Could it spark a meteor shower? Almost certainly not. Its dust trail doesn't line up with Earth, and the coma is too diffuse to form a dense stream. A few stray grains may wander in, but they would be too rare to notice. Brightness will also remain modest. For most, 3I Atlas is a telescopic object, a faint smudge in the eyepiece. With effort under dark skies, backyard astronomers may capture it, but it will not be a naked eye sight. In the end, 3I Atlas is not a threat, but a messenger. A modest visitor carrying the history of another system into ours. At first glance, the speed of this interstellar traveler may sound alarming. Near the sun, it races along at tens of kilometers per second, fast enough to cross an ocean in just a few minutes. But velocity by itself isn't a threat. That motion comes naturally from falling into, and then climbing out of, a star's gravity. What matters is distance, and the closest this object, known as 3I Atlas, will come to Earth is still far beyond the gap between Earth and the sun. Imagine a ship just past the horizon. Radar can detect it, but it remains invisible to the naked eye. Light from the sun takes about 8 minutes to travel 1 astronomical unit, and this visitor never comes closer than a dozen minutes of light travel time. That is not near by any reasonable measure. Gravitational forces work much like sound. Strong nearby forces are loud and constant. The Earth's pull that holds you to the ground, the moon's tug that moves the tides, and the sun's control over the planets. Distant forces are quiet. The gravity of a passing interstellar body, or the puff of gas from its surface, may be detectable, but they do not have the power to shift daily life. When considering risk, there are 3 questions. Could it hit us? Could it disturb our environment? Or could it fuel confusion? The first is ruled out. Its trajectory is well mapped and misses Earth by an enormous margin. The second is negligible. At these distances, tides, radiation, and magnetism are too weak to matter. The only real concern is the third. Terms like interstellar and fast can sound dramatic without context. Clear numbers and plain descriptions are the antidote. The path is wide, the light faint, the visit brief. 3 measurements frame the situation. An eccentricity greater than 1 confirms the orbit is hyperbolic. This object is not coming back. Hyperbolic excess speed shows that even far from the sun it carries leftover momentum, ensuring it keeps moving outward. Distance rules everything. Double the separation, and sunlight dims 4-fold. Double it again, and gravity's pull nearly disappears. These aren't obscure details. They are the foundations of why this event is safe. What will happen is straightforward. Telescopes on Earth and in orbit will record images and spectra during the best observing windows. Surveys will continue refining its position. Skilled amateurs may track it as well, sharing their results with professionals. For most people, nothing will be visible, and that is perfectly fine. The cosmos carries on whether we notice or not, and even a faint passage brings value. Every interstellar object provides data about how planetary systems form. Building planets is a messy process. Young giants scatter smaller bodies outward, some to distant reservoirs, some to dust, and some fast enough to escape forever. Visitors like 3I Atlas are direct proof of that scattering. Over time, the details accumulate. Systems with large migrating planets or companion stars eject more material. Those with only smaller closing planets eject less. The appearance of each visitor, whether dusty, quiet, icy, or inert, reveals where it may have formed and how it aged. The speed and direction of arrival add another layer, hinting at whether these bodies come from specific stellar neighborhoods or from a broad mix spread throughout the galaxy. Debris belts around other stars tell the same story from a different angle. They show what remains bound, while interstellar visitors show what was expelled. Together, they provide a fuller picture of planetary construction and waste. How many fragments are ejected per system is still uncertain. If few, then such objects are rare. If many, the galaxy is filled with them. The more we find, the more accurate our models of planet formation become. Small details matter too. If surface ices activate far from a star, the body likely formed beyond a snowline. If it remains silent, it may have been baked near its parent star or preserved for eons in deep cold. Binary systems, with their unstable zones, may create a different mix of travelers. Over years of discovery, these patterns will sharpen. Each of these objects is like a receipt from another planetary system. It may not reveal every detail of its birthplace, but together they build a map of galactic processes, showing how planets grow, how debris moves, and how stars shape their surroundings. The next generation of observatories will expand this work. The Rubin Observatory's Legacy Survey of Space and Time (LSST) will repeatedly image vast regions of sky, detecting faint moving points and confirming their hyperbolic paths quickly. Its wide field and consistent measurements will catch visitors earlier and track subtle changes more precisely. In orbit, the NEO surveyor will complement Rubin's work with infrared eyes. Even the darkest objects glow faintly in heat, allowing their true sizes to be measured. You can also watch near the sun's glare, a blind spot for ground-based telescopes. Together, these facilities will improve discovery rates, cut down false alarms, and give observers more time to gather spectra, light curves, and activity measurements. Even when they find nothing, the data still matters. If Rubin detects a faint optical source, but NEO's surveyor sees no heat, that absence sets a firm limit on size and reflectivity. Non-detections are as informative as detections. The conclusion remains steady. No impact, no tidal disruption, no harmful radiation. The real outcome is knowledge. Each new interstellar object adds to our understanding of how planets form and how galaxies fill with leftovers. 3i Atlas is one quiet dot on that expanding map, a reminder that the making of worlds always scatters fragments, and that with sharper eyes on the sky, we will catch more of them in the years ahead.